In this example, I will use a different type of satellite imagery, namely radar imagery, to delineate the shoreline. In this article published in the Times of India on February the 9th of 2023, it is mentioned that around 30% of the coastline of Andhra Pradesh, a state on the east coast of India, is suffering from erosion. Visakhapatnam as a district is suffering from the highest erosion, and nearly 26 kilometers of its coastline has been eroded. This will be our area of interest, and let me zoom into it on Google Maps. The city, which is Andhra Pradesh's most populous and largest, is also known as Vizag. One of its landmarks is observed on your screen. It's the Vizag port, which lies roughly at the center of its coastline. Also a very popular tourist destination because of its wide variety of beaches, which we will study and which you can see on the screen. Rushikonda is one of its famous beaches, as is Ramakrishna Beach and several others. Let me show you an article involving Rushikonda Beach, for you to gain further context. The New Indian Express had reported in this article from 2016 that the number of visitors flocking the popular beach destination of Rushikonda were declining rapidly because of the nature of the beach. And in July of that year, virtually the entire beach had been wiped out due to heavy beach erosion, spurring conservation efforts. Now, radar imagery does not appear like optical imagery, the kind of which we've used thus far. It does not look like a color photograph. Therefore, we can just glance at the topography and terrain characteristics of Vizag's coastline in order to aid our interpretation of the radar reflectance values later on. As you can observe, there is a distinct sandy, grainy texture surrounding Vizag's coastline, besides the standard features such as waves hitting the shore and so on. As a next step, we'll visit geojson.io, a platform that I've even used in my previous workflows, in order to download the area of interest coordinates in a WKT file format, a well-known text file format. I have zoomed into Visakhapatnam on the map and will draw a polygon over it and hit the save button and save it as a WKT file. This WKT file will be useful for us in a couple of junctures later on in our workflow. Let me save the downloaded file onto my working folder. This file can be opened in a notepad, and it just contains the coordinates in a text format, as you can see. As a next step, let me visit Copernicus browser, a platform that we've used previously before to download the Sentinel optical imagery. This time we will use it to download the Sentinel satellite constellations radar imagery. Now, we don't need to zoom into our area of interest. We just can upload the WKT file and it will straight away zoom into our area of interest. Subsequently, we'll go to the search button and select the Sentinel-1, which is the radar imagery. It captures information in CSAR. CSAR is meaning C-band of synthetic aperture radar. You can pause the video over here if you wish to read a fact sheet about Copernicus Sentinel-1 platform. It's when was it introduced, as well as what are its applications at users. Now, why are we using this particular workflow of radar imagery? It has certain distinct advantages over optical imagery. So optical imagery, you knew, were influenced by clouds and was impacted by weather conditions. But radar imagery, because the source of illumination is the sensor on board the satellite and not the passive illumination such as sun when it comes to optical imagery, we can basically obtain the images even at night time and even if there is a cloud cover. So the radar rays, the C-band basically pierces the cloud and the reflectance values are also not affected. Now, we will capture the imagery in interferometric wide swath mode, which has a resolution of 100 meters. So 1 pixel is equal to 100 meters. So this is one of the disadvantages because the resolution is not that high, but then There are certain advantages of using Sentinel-1 imagery as well, just as I had stated before. We will use level 1 ground range detected product, and in the filters box I will select interferometric white swath as my acquisition mode and vertical transmit vertical receive plus vertical transmit horizontal receive as the polarization. Next we'll select the time range. I am doing a temporal analysis and I intend to use radar images from 3 distinct time periods 4 years apart. So let me download the first set of radar imagery first, which is from the current year of recording 2024. I select a 15-day time period from April to May. Copernicus browser throws me 3 search results over which basically overlaps my area of interest polygon. One imagery completely overlays on top of it while the other intersects it. So I will be more interested definitely on using the former, which completely overlays my imagery, which is the second imagery from the search result. Let me go to the product info section. The imagery has been captured on 29th April of 2024. That is okay, but what I'm more interested to observe is what is the relative orbit number. Because I'm doing a temporal analysis and I wish to basically make the area of interest, you can say the radar images, consistent over the 2 other timeline which I will be downloading the product later. So if I know what is the relative orbit number, which is which cycle in which the satellite has captured this imagery, that particular number is the unique identifier which remains consistent over over the cycle of the satellite on any given day. So now let me select a different time period, which is from 2020. Now this similar timeline. One added step which we'll adopt this time is to input the relative orbit number in the filter section. I will key in 90 because that is the RON which I'll be interested in, and subsequently I'll hit the search button. There are 2 search results. One is from May, 8th May, and the other one is from 26th April. Now, unlike optical imagery where we used to observe the cloud cover, we don't need to do this for radar imagery. So I'll just click any one. I'll select any one of the product and add that particular product onto the workspace so that I can download it later. Thereafter, I'm selecting a similar time period from 2016. There is one search result which is captured on 5th May and I'm just adding it to the workspace once again. The workspace can be accessed from here and it contains all my previous history and which products I have earmarked. So these 3 products I had earmarked. I have already downloaded it onto my system previously, but this is how you basically hit the download button. These are large files, nearly 2 GB each, so it will occupy space. The zip files, as I have indicated, I had downloaded and saved it previously in my working folder. These are fairly large in size, so you need to have sufficient bandwidth on your hard drive. Let's open Sentinel Applications platform, the Snap software, to post-process this raw radar imagery from the Sentinel coastline of satellites floated by European Space Agency, which are very useful for Earth observation purposes and which we'll use for delineating the shoreline. Upon clicking the bands of one of the product, this is how the imagery looks. See, it does not look like a normal photograph. It just contains the reflectance values of the radar, C-band radar, which the satellite's transponder had thrown on the Earth's surface and which the receiver on the satellite had captured the reflectances of. So there are 2 distinct bands. One is the amplitude and the intensity. And if I go to the pixel info tab, I can basically see what is the value over that particular pixel. And I've indicated that each pixel is basically 100 meter in resolution. So amplitude is captured in VH as well as VV polarization as I had selected. And the same applies for the intensity band. Let's begin processing the imagery, first by developing a graph using the Graph Builder tool, which will contain a set of sequential processing steps. The subset tool will be our first processing step. It will help Snap to do faster processing, as it will clip the dataset to only our area of interest, thereby limiting size of the dataset considerably. Subsequently, the Apply Orbit File tool will help Snap to update the metadata of the dataset by obtaining the precise velocity and position information of the satellite when it had captured our imagery. Subsequently, the Thermal Noise Removal tool helps Snap to remove the inherent background noise of the satellite's receiver. The Calibration tool helps Snap to assign the reflectance values to the precise pixels on the map view, thereby facilitating quantitative analysis. Subsequently, the Speckle Filter tool helps Snap to remove the inherent salt and pepper texture which is present in the raw imagery dataset. And finally, the Terrain Correction tool helps convert the dataset, which is in a geographic coordinate system as standard by default, into a projected coordinate system, thereby making it usable for further processing on other GIS software. We will connect the graph, and this is the set of commands needed to convert the input into the output. However, if you face an error, just as in my case, feel free to split the graph into two distinct graphs, which will basically remove the error, and you will be able to perform the tasks also. Instead of individual processing using the Graph Builder tool, we will batch process all the three files together. So once I open the batch processing tool and add all the three files, what we will do is load our graph. I had split the graph previously already, so we will first do subset apply orbit file only. So in the subset, as you may be familiar from the previous workflow as well, we basically select the bands which we require. This time we will only require the VH polarization bands, so we will only keep that. And in the geographic coordinates, we have our WKT file which contains the precise location of our area of interest in a WKT form. So we will just update it, and as you can see, the yellow polygon indicates our area of interest. In the apply orbit file, we will just keep everything as default and also click the do not fail if orbit file is not found information. So once we have it and we determine the correct directory, we can run the tool. The tool doesn't take too long to run, depends on the system to system. So once the output is generated, I can show you what the output is, but typically it is not needed because we can run the entire processing steps in one go also, which we were unable to do this time. So the output contains the amplitude and intensity information in a VH polarization. So I'm opening all the files, and in case you want to read the data pixel values or just compare it side by side, you can feel free to do so if you are doing this workflow yourself. Now let's proceed to do the second part of the graph, again using the batch processing tool itself. So now we'll have to use not all the 6 files, but only the 3 output files from the first processing step. So we'll first remove the raw imagery dataset. So we are now left with the processed files. Subsequently, let me load the graph. We'll do thermal noise removal, calibration, speckle filter, terrain correction in this step. In thermal noise removal, we will only select the VH polarization. We don't need the VV polarization. In calibration, we will leave everything as default. The speckle filter, we will also leave everything as default. We can select the sigma naught band. In the terrain correction, there are a few steps which we need to do. First is select the band. Subsequently, instead of 3 sec, which is of a lower resolution, we will select SRTM 1 sec HGT. Next, I'll uncheck the mask out areas without elevation box. By default, masking areas without elevation would essentially mean masking out the water pixels from the dataset, thereby leaving only those pixels attributed to land. Conceptually, this is a beneficial outcome when it comes to coastal erosion. However, I have removed this step after much deliberation because I feel that the low resolution SRTM elevation dataset that Snap uses to do the masking is from the early 2000s, and hence it is old. It does not represent the current reality very well, and I strongly suspect it leads to erroneous masking. The final step in terrain correction, what we will change is basically convert the map projection from the default geographic coordinate system of WGS84 geographic lat long to a projected coordinate system of UTM WGS84 automatic. The map projection automatically switches to zone number 44, which corresponds to our area of interest. If you remember our previous workflow using Sentinel-2 imagery, the area of interest which lied on the west coast of India fell under zone number 43. This area of interest is on the east coast and falls under zone number 44, which Snap automatically detects and pastes it. Finally, the write command, we just have to check whether the name and directory correspond to our preferences and hit the run command. Depending on system to system and the number of imagery that you are batch processing, it will take a reasonable amount of time to do this particular step. For the inputs number 4, 5 and 6, now we have output numbers 7, 8 and 9 published by Snap onto the Product Explorer view. This time around, there is only one single band of output which has been published, sigma naught VH band. Straight away, do you notice the similarity of this view? Have you seen it somewhere before? Let me show you. This is how the imagery looks on the optical imagery as well. Now you may wonder what's the big deal about it. By default, if you were to skip the video to a previous timeline, you will see that because how the satellite had captured the imagery was inverted and a different, you can say, angle. And now because we have applied the terrain correction, it is in the right angle as depicted on a globe, on a map view basically. Now what we are doing is on the pixel info tab, we are observing the values. Now this is a very important step because straight away you can notice that the land pixels would have a different value and the water pixels would have a different value. Now radar imagery, how it works is the water pixels are typically you can say have low reflectance value. So hence they are darker in shade, whereas land are higher in reflectance and therefore they are more whiter in shade. Now what essentially we want to do right now is to remove the black pixels completely from the data set. Thereby we will only be left with the land pixels and which will allow us to delineate the shoreline. So in order to identify which is the correct pixel value which corresponds to the water pixels, we'll just have to do some manual exploring. So we can see that the intensity of the dark at the absolutely jet black pixels lies anywhere between 0 to 0.005, 0.0043. So 0.005 and below is, in my assessment, where the jet black pixels are located. And any pixel value above 0.005 is, firstly, you can say, slightly in those hazy white spots, and we are currently ignoring it for the time being, and you can say pixel values of above 0.1 are corresponding to land that we are reasonably sure about. So for this particular workflow, this particular demonstration, let's use 0.005 as our you can say threshold which we will use to delineate. And now I would like to circle back to the point we had observed the topographical characteristics, and you can see that the semi-white, semi-black pixels correspond to that particular hazy nature of the beach, of the portion of sea adjacent to Vizag's coastline. So nevertheless, I mean, I'm not being too picky. I'm just masking out the absolutely jet black pixels by performing a new step which is called using the band match command on the existing band. So on product number 7, which is from 2024, I'll right click it and go to band match. I'll name the product as the landmask, and I will input a expression which will basically do some quantitative analysis and which will leave out all the water pixels and leave only the land pixels. So the command which I will use is, if the value of sigma naught VH for that particular pixel is less than 0.005, then make it as NaN, which means no data value, and else make it as 1. So essentially I'm saying if it is a water pixel, then mask out those pixels, and if it is not a water pixel, then make it bright white, thereby allowing for easier demarcation. So as you can see, the output has been generated. While this output is certainly easy on the eye and is convenient for post-processing as well, just in case you wish to test the accuracy of the applied thresholding, one can do so by using a slightly modified formula. Let me show it to you by creating a new band for comparison. I'll name it as test, and instead of the land pixels being marked with a value of 1, I'll ask Snap to keep the land pixels with the original sigma naught value which was generated in the previous output. Let me show you the new band result. What we'll be keen to observe is the edge of the coastline. If our thresholding is correct, there should not be any discernible jet black pixels. But in our case, as you can observe, there are still a few jet black pixels. Using the pixel info tab, we can observe the intensity. It is slightly higher than 0.005. So it is like 0.006, 0.0075 and so on. So in an ideal world, we have to basically modify our thresholding in order to get an appropriate result. But for this study purposes, I'm not changing it. I'll keep the threshold as the 0.005 which we had originally selected. Let me delete the test band and create a new landmask band using the same thresholding of 0.005 to keep the methodology consistent across all the 3 data products that we are using from different timelines. The output is quick to generate. Also, remember to uncheck the virtual box because that will not save the product. By unchecking it, it will save the product. Now we are basically done the post-processing on Snap, and we'll have to export this particular output to our system so that we can further process it using ArcGIS software. We can use a different software if you like also, but I prefer using ArcGIS. The way to export the product is by either going to File and Export and exporting it as a GeoTIFF, which is basically a geolocated image file, or you can right click on the image view and click on Save as Image, click on Full Scene and Full Resolution, name it as you like and save it as GeoTIFF and hit the Save button. So we've done so for product number 7, which if you observe is from 2024. We will replicate the same step for products from 2020 and 2016 as well. Meanwhile, in case you are wondering what are those black pixels on the white land and the white pixels on the dark sea, those are basically certain water bodies, small water bodies on the land as well as tiny, objects on the sea. I think that's the only possible reason why it is, or maybe it could be a certain noise and backscatter as well, but I think it is more likely the former. Now, we have saved all the 3 output files as GeoTIFF, and we will proceed to basically do the next steps on ArcGIS Pro. Let me drag and drop the 3 products onto the map view on the contents pane of ArcGIS Pro. All the 3 products have been loaded. I'll just choose to minimize the expanded view as I do not want extra information on my eye line. One thing which I missed informing you is that while we had used the website geojson.io to download the WKT file format for our area of interest, we can do the same step from within Snap itself. All we need to do is draw a polygon over the area of interest and right click on it to obtain the WKT from geometry. We can copy and paste it in our text file to use it for further, processing steps as well. Also, while we had proceeded without masking the water pixels by using the SRTM elevation band, let me show you how it works and what is the result like. We'll go to raster and go to masks and select the land sea mask function. Within that, we'll select the product which we want to basically apply this command on. Ensure that the directory is correct where we want to save it. Select on the source band. So we want to use the land mask band where we did not use the elevation earlier, but we are now using it. We'll select mask out the sea and use the SRTM3set digital elevation model to perform the, masking out of the water pixels. Let's see what the output looks like. Just to let you know, a digital elevation model is basically bare earth, elevation model. So it does not capture the height of the features on top of the earth, let's say a tree or a building or something like that. It only captures the height of the bare, you can say, ground features, bare earth features, that is. So this is the output which has been generated after performing the masking by the SRTM model. So you can see the white pixels over the water body has been completely eliminated because those were part of the no elevation, you can say, data set which was obtained by SRTM mission. Coming back to ArcGIS Pro, once again, we are now ready to perform the next processing steps. And as I had indicated to you before, you do not need to worry about those white pixels which you see on top of the sea. We will remove it in one of our next steps as well. So the first geoprocessing tool which we will use on ArcGIS Pro is the raster to polygon command. This is something which we had used in our previous workflow involving Sentinel to imagery post-processing as well. All we are doing is converting the individual pixels into a polygon shape. So from a raster to a vector file is what we are doing via this geoprocessing tool. We have performed this tool for 2024 product. We will repeat it for 2020 and 2016 product as well. As you can see, upon clicking on it, there are distinct shapes which are being selected instead of individual pixel values. Upon opening the attribute table, you can see that there are 1339 distinct shapes in the particular area of interest. Now that is large because of the several small tiny pixels on land and tiny pixels on sea. The figure of the number of, you can say, objects is high because of that. But otherwise, the two main objects are, you can say, the one with the largest shape area, and we will choose to preserve one of them in one of our next processing steps. Our next task is to isolate the appropriate polygon shape which contains the shoreline in its entirety from the polygon layer, and further convert this particular shape into a polyline layer which would allow us to isolate Vizag shoreline. However, we are unable to run that tool which we typically use, the polygon to line layer, right now because our current polygon shape is too complex and comprises of multiple attached and overlapping shapes. Instead, we will use an intermediary step, feature outline mask. We'll select our input layer and set an appropriate reference scale, in our case 1:100,000, and set an appropriate coordinate system and run this particular tool. So what this tool essentially does is it creates a simplified polygon outline layer, and the result can be evident once we explore the attribute table. So once we click on the polygon, you can see the pop-ups. We are able to see that visualize the particular polygon which we would like to extract. So it can be separated in its entirety now. And upon exploring the attribute table, you can also observe that when previously we had nearly 9,000 shapes, right now after running this tool, we just have 1,661 shapes. And obviously the second, you can say the second shape is the important to us as it comprises of our shoreline, and we can basically isolate it from this particular list. How we do that? We press Ctrl Alt. We just leave the second object ID and which contains our polygon of our choice, and delete everything else and hit the save button from the edit tab. So we have isolated the polygon of our choice. Similarly, we will repeat this step for the other two layers, 2020 and 2016, that is. The margin of the outline, we keep it as a very low figure, which is 1 millimeter. So essentially, we are not tampering with the layers properties, just we are creating a simplified outline. Once again, the second largest feature contains the polygon of our choice because we can see the shoreline of Vizag from it. So we'll keep that, hit save using the edit tab. Finally, for 2016, we will repeat the same process. And hit the run button. In the attribute, there are just 850 attributes, and once again we'll sort it as per the descending shape area. The second row is of importance. We'll keep it, delete everything else, hit the save button. So now we have the polygon of our choice for all the three timeline of our study. And instead of a filled color symbology, we will change it into a outline because they are actually outline of the, you can say, area of interest. We will also color it in a different color so as to basically distinguish from one another. There are a variety of shapes, sizes, dimensions, colors, thickness we can basically play around with to obtain the preferred, you can say, symbology of the layer. Now then, we've completed playing around with the symbology, and frankly speaking, this is not very important for our workflow. Just for visualization purposes, I have done this step. Our next step is though very important. We are now in a position to use the tool which we could have used earlier, but we are using it now, polygon to line command. This will basically break down the polygon layer into polylines, and we will further extract the shoreline from this particular generated output. Let me repeat this geoprocessing tool over the remaining two input layers from different timelines. We can choose to name the output files as per our choice. By default, it saves in the project's geodatabase. So the new output has been generated, but you will not be able to spot because they look, quite frankly, same as the previous output. But then once I switch off the older outputs, you can see that the new shoreline has been generated. And these are individual lines, and if I zoom out and if I click on that particular line, the entire shoreline is being basically selected. Now it's not necessary that the entire shoreline can be selected. Maybe some of the times it breaks down into multiple shorelines, but in our case we are fortunate that the polygon basically houses the entire shoreline. Once again, we don't want the other outlines, we just want to preserve the shoreline. So we'll just select that particular, once we use the descending order on the shape length, we find that there are certain simplified, you can say, polylines which we do not want to keep. So we are only interested to keep the largest polyline, which is basically the outline of the entire area of interest. So we'll just keep it and delete everything else. That is one option what we can do. But what we will do instead is not complicate the procedure that much. We will just directly use the split tool. So once we select the largest, you can say, polyline from within that layer, we will use the split command and create two crosses across the area which we want to cut off from the main shape. So now the shoreline is highlighted because we have cut it off from its two ends. Once we go to the attribute table, you can see that the shoreline shape has been extracted. We can just click on that particular row and see. So the largest shape of the line is of the other outline, but the second largest one corresponds to our shoreline. So we'll delete everything else and just preserve the second largest polyline, which we have artificially, you can say, cut off from the main shape. We've saved this and our new shoreline has been generated. So this is the output that we were craving for when we had initiated our study. So let's examine it. Is the shoreline accurate? I'll say it is reasonably accurate. Remember that our thresholding was slightly off the mark. So keeping that in mind, if we would have put an appropriate thresholding, maybe the shoreline would have been very, very accurate. Right now, it basically mimics the shape of the shoreline, but it is located at a certain distance away from it. But it's sufficient for you to know that this method works, and this is how the output looks. So now that we are familiar with what the processing steps are, we'll repeat it for 2020 and 2024 layer as well, very quickly. Sort the shape length column in descending order. We want to preserve the largest shape, so we'll select it and we will split it so that we will cut off the unnecessary ends and just keep the shoreline as a separate row, which we will isolate and delete all the remaining features. Remember to keep saving your file from time to time. And even when you make edits, you don't have to save the project, you have to save it from the Edit tab. So we've created the new shoreline. We've extracted the shoreline, that is, from 2020, and we'll now do it for 2016. In case I am speaking too fast, you can play around with the YouTube's play speed and reduce the play speed so as to make the content much more easily audible for you. In any case, the subtitles are there for you to basically have a guide for the workflow. Right then, we are done with creating all the 3 shorelines. The thing is, we are not able to very clearly spot them. So again, we can modify the symbology so as to demarcate one shoreline from the other, and then we will try to interpret what the results are. So 2016 layer, we'll color it as green. So the oldest timeline is green, the middle timeline is yellow, and the newest timeline is red. In this way, it would be easier for us to interpret. Now let's navigate around the coastline and see how the output has come out and what we can basically interpret from it. Remember that we are just creating a visualization. So initially we did it in a, you can say, visual manner. Right now we have created a shoreline using Sentinel-2 first and now on Sentinel-1. And in our subsequent workflow, we will also measure the net change in the coastline. So in case you are wondering, that comes next. So there is an evolution of that. Now I have blanked out the 2020. So I'm currently only comparing 2016 with 2024. Around the edge, the green line, which is 2016, is closer to the beach. So what it essentially shows that there is accretion on this particular side, although in some areas there is erosion. Actually, what happens is wherever there is urban infrastructure which is created near or within the sea, there is a updrift, downdrift, which basically impacts. So typically wherever there is a port, there are certain areas on, let's say, downdrift would face accretion and certain areas on the upstream will face the erosion. So on the northern end of the port, you can see that there was a significant erosion. But on the southern end of the port, the beaches which are located south to it, there was reasonable, you can say, accretion. Remember that the news articles which I had showed to you initially at the beginning of this particular, you can say, subset of video, those were referring to the timeline around 2016. So subsequently, there has been change, and as you would have known that there were certain conservation efforts too, which could be the reason behind accretion. This was how Rushikonda beach was, and as you can see, the news article was published in 2016. But subsequent to that, there is a certain, you can say, accretion around that particular beach. So just FYI, the erosion and accretion are just natural phenomenon, but the rate of erosion and accretion is something to worry about. So erosion by itself is not a negative aspect, and it can be restored, and it's a natural phenomenon. Meanwhile, let me show you, while we have you can say automatically created a shoreline, there is also a way to manually create a shoreline. Now, depending on case to case, you may choose whether to use the automatic way or manual way. So in the manual way, you just have to create a new feature class from the catalog pane. You have to right click on the geo database and create a new feature class, and subsequently you add a line on top of the edges of the white pixels. This would kind of give you a representation of the coastline. Now obviously, because our area of interest is too large, this is not appropriate step. However, if you want to basically observe, you can say, with more accuracy. I can't say more accuracy, but in a more detailed manner, a particular beach, then perhaps this way would be suitable for performing that kind of analysis. Also, while we have used SRTM dataset and it has a resolution of 30 meters, I just wanted to let you know that there is also ALOS Pulsar, which is captured at a later date, 2011 onwards, and that is of a reasonably higher resolution. You can get it from this website, search.asf.alaska.edu. You have to create a login account and create a polygon and search for the DEM layer. The high-res dataset is of 12.5 meters resolution, which is significantly better than that of SRTM. However, we are unable to use it in Snap directly, although we can use it in ArcGIS Pro to basically mask out the water pixels. So as you can see that 2006 to 2011. So it is relatively newer and obviously newer than SRTM. So this is another aspect which, before closing down this section of the video, I wanted to bring to your attention. This ALOS Pulsar is by NASA Earth Data. I hope you like this demonstration, and apologies if I have made any errors in communication. Thank you. Let me switch to the default view on ArcGIS Pro, which is the topographic base map.